So, hello everyone again and welcome to my channel. On our previous video, we talked about kinetic energy and how kinetic energy can be used to generate its operator using various interesting quantities like, for example, momentum, both in classical mechanics and quantum mechanics, in order for we to generate its operator, which is the kinetic energy's operator. Now, we also focused on introducing one-dimensional case for our operator in kinetics energy and also the three-dimensional case. Now, the three-dimensional case is actually called the Laplacian operator, and this Laplacian operator transforms your one-dimensional situation to a three-dimensional situation by introducing the d squared over dy squared plus d squared over dx squared plus d squared over dz squared. Now, in this video, we're going to specify how we can actually detect our operator and also detect our observable when we introduce our eigenfunction and also resulting in our eigenvalue. Now, of all measurable observables made by the operator represented as this, the ones that are more observable are called the eigenvalue, which is represented as A. But anyways, this A doesn't have this, so I just going to cancel it because we don't need that over there. So in here, this is our operator and this is our observable over there. Now, in terms of representing it in a general formula, our general formula or notation is actually in the form of F equals to small a, which is our observable, multiplied by the same F over here. Now, what does all these particular variables over here, what do they represent? Now, first of all, this A over here represents our mathematical operator and while our F over here represents the operator applied to a function called an eigenfunction. Now, the other case side over here, which is our A, small letter a, represents the results in an observable, which is called the eigenvalue. And while this our F over here represents the function which is still reproduced after you apply this function to another operator over there. We still generate our function after that particular calculation over here. So this is reproduced after we apply that calculation to another operator. Now, since we're able to actually label all these particular variables in there, now some combinations of operators and functions would actually regenerate the same function. That is how we are going from here to this same function over there. Now, an example of this is looking at this particular formula where we have dE 2x over dx, where we are looking at the x coordinates over here. Now, if you're calculating this, what can we do over here? We know that the derivative of e2x is equal to 2e2x, where we get this as a result then multiplied by our 2 over here. Now let's label this with respect to this particular formula system over here. What we do notice in here is that this d over dx is actually called our operator, which is our a bar over there, and while our e2x is actually called our Eiganfunction. Why am I calling it an Eiganfunction? Because this is actually reproduced at the end over here, which is what we got over there. And while our 2 over there is actually our eigenvalue, which is the numerical constant of the eigenfunction. So that's about it for this particular video. I hope you're able to understand how you're able to separate the operator from our result, which is our eigenvalue, and how we can actually look for formulas that truly represents an eigenfunction. When you apply it to an operator, we get to our product where we regenerate our eigenfunction over there. So thanks for following me through this. Really appreciate it. See you on my next video. Be smart. Bye.